little bit about myself. I'm a member of the Buffalo Astronomical Association. It's a group of amateur astronomers. It's been in existence for over 70 years. And I joined in May of 2009, so I've been there about 10 years. And I do contribute to the newsletter. I write most of the technical articles. There's other people in the astronomy club who know more than me, but I don't know why they don't contribute to the articles. So far, I'm the one who writes most of the articles. Been doing it, dozens of articles for 10 years. So in the course of my study, I discover a lot of things. And one of the things I like to present here is that the universe is designed by God. And despite what the atheists tell you at the university, I can prove it through geometrics, and I can prove it mathematically, and I will prove it mathematically at the end of my speech. All right?
Cool.
Woo. Okay, let's begin our study here. The theme of my presentation is the heavens declare the glory of God, and I get that from Psalm 119, where it says, "The heavens declare the glory of God, and the firmament shows His handiwork." There's three things that give background. God reveals Himself three ways: through the written word, through the testimony of conscience, right or wrong. Everybody, no matter what ethnic or nationality, has an intrinsic sense of what's right and wrong. This has been proven by sociologists. They went to tribes in Africa and everything, and they give is adultery wrong? And every one of them said yes. Is stealing wrong? Everyone. Yeah. That's a testimony of conscience. God gives us. It's intrinsic. And the third way is called the book of nature, and that's the birds, the bees, and the stars. And the ancient Greeks were familiar with that. They didn't believe in one God, they believed in many gods, but they studied nature, and they came up with the idea, too, that there's something divine about how things are constructed. And it's in the book of Romans, it says, for chapter 1, verse 20, it says, "For the invisible things of Him," that's God, "from the creation of the world are clearly seen, being understood by the things that are made, even His eternal Godhead." And here's a cleanser, so that they are without excuse. So these atheists who say there's no evidence of God, they're denying their conscience. They're lying against the Bible. Have you heard of? There's a man. He's the most famous atheist scientist. His name is Richard Dawkins. Have anybody heard of Richard Dawkins?
Oh yeah.
He goes around to colleges and universities. He's written books. One is called The God Delusion. He says there's no evidence. There's absolutely no evidence of God's existence through creation. So one of the reporters said, "What if you're wrong? What if you die? When you die, you come face to face with God. What would you say?" He would say, "Sir, why'd you make yourself so invisible?" Well, I'm here to prove that God didn't make Himself so invisible, and one of the major ways is studying astronomy. And we're going to begin our first thing. We're going to let's go to the sun. Picture number 1. Okay, this is our sun. It's our nearest star. It's about 93 million miles away. It's 109 times bigger than the Earth, so that means 109 Earths can fit inside it. Most of the sun is 75% composed of hydrogen. The rest, a little less than 25% is composed of helium, and the rest is composed of lithium, hydrogen, all the way up to uranium. The way the sun works is that it fuses the materials. The hydrogen is fused in the center of it because there's so many. It's so big that the pressure in the core of the sun, 380,000 miles from the surface to the center, it fuses it into the first product is helium, and then it refuses things. It goes into lithium, it goes into calcium, and all the chain down to uranium. That produces high energy gamma rays. These high energy gamma rays, that's where the light comes from. It comes from the core. It doesn't come from the surface. So the high energy gamma rays zigzag their way because there's so much pressure. It zigs their way up to the top, and as the high energy gamma rays zigzag their way up to the top, they lose energy. And then once they reach the top, there is visible light in the visible spectrum. X-rays are still produced through magnetic storms on the surface a little bit because they have X-ray telescopes in that. So that's how it's produced. The sun produces the amount of energy to produce those gamma rays is equivalent to 3 billion hydrogen bombs exploding every second. So here's the illustration of the sun there. Can you see the right there. These are the, this is like a prominence. There's a little fire shooting out. It's actually plasma, it's not fire. It's, super hot gases, when they get to a certain degree, it turns into plasma. And so these are prominences. I've seen these through the telescope. This is a solar flare. Now, when you see pictures on TV of the solar flares, you can see them, shooting upwards. That's time-lapse photography, because I've seen it live through telescopes, and everything looks stiff, like they're not moving. It looks like it's not moving, and the reason why it looks like it's not moving because the distances are so great. They're moving at 5,000 miles an hour, and this is hundreds of thousands of miles long. These short prominences are. It looks like they're right on the surface, but they're 10,000 miles high. What's more, in these prominences, the whole Earth can fit inside it, the smallest part. So the sun is very big. Surprisingly, it's called a yellow dwarf. Why is it called a yellow dwarf? It's because compared to other suns, it's small. And the reason why it's called a yellow dwarf, not because of its yellow color. That's a misnomer. People think that it's called a yellowish color. It's yellowish color in its spectrum, not when you look it up. Not when you look at it in the sky. It's a spectral color. All right. But what's not so small about the sun is that even though it's a common star, many stars in our solar system are like our sun. Same composition. We can tell the composition. We can tell what type of stars are by their spectrum, and the spectrum contains lines. They're called absorption lines. Different chemical elements absorb certain wavelengths of light, and they show up as lines. And so, when you go to the store and you buy something, you get a barcode. It's a pattern of the barcode. Each sun has a different barcode. We can identify different types of stars by the different barcodes. There's more than 1,000 different types of stars, so the sun is a very common star. But what's so not uncommon about the star is they've studied for more than 40 years all the thousands of stars just like our sun, and our sun is the most stable of all the stars like it. Isn't that something? Stars are like our sun. It's a G2 star. G, the letter G, the alphabet. Stars are designated by the letters of the alphabet. Our sun G designates it. It's not old and it's not young. It's right in the peak. And the number 2 has to do with energy production. Technically, the energy production is a little lower, but that's a technical matter that professional astronomers deal with. Okay, but what's not so unusual about our sun, what's so good about our sun, not so small about our sun, is of all the stars, thousands of stars like our sun that we studied, ours is the most stable. It burns at the most steady rate. If our star was a little bit smaller, it would flare more. Flaring more. This is an example of flaring. Shooting up, and when it flares, it goes to excess magnetic particles. Smaller. If our sun was smaller, it would flare more. If it was a little bigger, it would flare more. Flaring, it's like a flickering light bulb. You get more, and then you get less. You get more and less. So our star is just the right size. It's the most stable. It's the most stable of all the stars, like G stars. It's called a main sequence star. It's hydrostatic equilibrium. About the energy that's being burned, the force that's going into the core is almost equal to the force that's going out. But the force going out is slightly more, but for general amateur purposes, we consider it equal. Okay. Well, a byproduct of the sun is magnetic radiation. On the core of these things, this is hydrogen, and it's rubbing against each other. They're moving at different velocities, and as the hydrogen rubs against each other, it creates we could call it static electricity, only huge amounts. And then this is a flare. This is sending out a lot of electromagnetic particles. Millions of tons of electromagnetic particles go toward the Earth every day at velocities between 800,000 and 2 million miles an hour. So, all right, so The bad thing about electromagnetic particles is they can strip away the atmospheres of planets. Now let's get a picture of the Earth's magnetic field. Well, lo and behold, the Earth has a protection. It's called an electromagnetic field, otherwise known as a magnetosphere. And in the center of the Earth, it's liquid iron. The Earth is spinning, and as this iron spins, it creates electrical field. It's like a dynamo. Create electricity. You spin a magnet around copper wires. It's the same principle. It is concentrated. It's in the center. The magnetosphere surrounds the whole Earth, but it's concentrated. The positive and negative. It's concentrated at the poles. So when the sun's particles hit the Earth, they're directed towards the poles. They do hit the atmosphere here. They hit the atmosphere here. And you could see sometime in a clear night. You could see at certain times of the year. You could see the aurora, which I get to. And you can see it in Lockport, New York, and I've seen it. But mostly it's concentrated right in the northern and southern portions, and it interacts with the oxygen and the neon in the atmosphere. Neon produces green, oxygen produces blue color. All right. It does strip away the atmosphere a little bit on the Earth. It does strip away the north and south pole atmosphere, but it's so minor that it's inconsequential. So that's an example of how the Earth is protected. Now let's get to the Earth and the Moon. That's a picture of that. That's a picture of the aurora. In the South Pole, it's called the aurora australis. And other planets, we've seen that in other planets. Jupiter has the northern lights as well because they have a shorter magnetic field. Mars has a weak magnetic field. It used to have an atmosphere. I saw pictures before it was broadcast to the public of the water on Mars. They used to have water on Mars as big as the Atlantic and Pacific Oceans. That evaporated because of the atmosphere. It was a thin atmosphere at one time, and because the magnetic field was so short, the magnetic field of the sun, the magnetic particles stripped the atmosphere of Mars. Mars still has an atmosphere, but it's so shallow. So Mars used to have atmosphere. Mars used to have an ocean as big as the Pacific Ocean and the Atlantic Ocean. We could see that. We know that because we could see the erosion of water. And we can still see water spouting out from time to time. Okay, now this is a picture of the Earth and the Moon. I don't know if this is a photograph or an illustration. I've seen plenty of photographs. It looks basically the same. As you can see, the Earth this is the Earth. Interesting thing about the Earth is, it looks perfectly round. It's not perfectly round. The southern hemisphere is bigger than the northern hemisphere. This is an exaggeration, but the Earth is somewhat shaped like a pear. You don't notice it. It's so slight. And there's a reason why the southern hemisphere is bigger than the northern hemisphere, is because the southern hemisphere needs more water and it needs more surface area to cool off the water. That's why it's bigger. That's divine design. Wow. Okay, so you can see the moon. The moon average distance is 238,000 miles. The Earth is tilted at a degree of 23.5 degrees. What's the purpose of that? It's the seasons. Does anybody know why we have the seasons? Seasons is to balance the temperature of the Earth. In the summer, right now, our northern hemisphere is pointing towards the sun. It's heating up. And the southern hemisphere is pointing away. It's cooling off. So we need approximately 6 months for the southern hemisphere to cool off, and alternatively we need 6 months for the northern hemisphere to cool off. And it's balanced at a degree of 23.5. That's a perfect degree. Because if it was tilted any more away from the northern hemisphere is tilted any more or tilted any closer, the seasons would be scorchingly hot and too cold. So now the Earth wobbles. It's called the precession of the equinoxes. It's like a top. When you spin a top, when it's just about to quit, it wobbles a little bit. Now the Earth is wobbling. It's not spinning perfectly. It's wobbling. And if that were to wobble after a while, it would wobble uncontrollably, and it would turn into a 60-degree angle after 13,000 years. But we have something that protects the Earth from doing it, to stabilize. Anybody know what that is? It's called the moon. The moon stabilizes the Earth's axis to keep it stable. You know, the moon is 1/4 the size of the Earth, and there was a British astronomer. He calculated if the moon was half its size, it would still keep the Earth stable. So the moon. We have the magnetic sphere, protects the Earth from the sun's dangerous magnetic rays, and we have the moon that keeps us stable. So we have moderate climate, livable climate, and that's due to the moon. There's another thing that the moon does that's very helpful. Does anybody else know what the moon does?
Tides, waves.
The moons control the tides. The sun actually controls the tides to a lesser extent, but the moon is the majority of the tides. And the tides wash on the coastal areas. Pollutions, dirt and stuff build up on the coasts, and that needs to be washed out. And the tides, the water comes in, and it washes the pollutants off. So the moon is also a cleaning agent. So that's pretty good. Let's go on to the next one here. And we're going to Jupiter. Jupiter's the biggest planet. It's at a mean average distance of 489 million miles, which means when you look at Jupiter, you're looking at it about, it was a half hour ago. It takes the light half hour to get there from Jupiter. Jupiter is composed mostly of hydrogen, you know, and it has an liquid aluminum core. It's a gaseous planet. Aluminum is 800 times bigger than the Earth, so 800 Earths can fit inside Jupiter. Jupiter is called a failed sun. If Jupiter was Jupiter is 1,000 times bigger than the Earth. If the Jupiter was 10 times bigger, it would be a burning sun. So it's sometimes referred to as a failed sun. Jupiter does a very important thing for our Earth, and it offers protection. And what is that protection? Comets and asteroids are always there's like over 100,000 objects in the asteroid belt. We know, astronomers know each and every single one of them, and we know each and every single one of them's location, and we know each and every one of them's velocity at every hour of the day. So there are always these particles from time to time, they go towards the Earth. Well, what does Jupiter do? Jupiter has a huge amount of gravity. What's the purpose of that? It draws these particles away towards Jupiter. If the particles are going towards the Earth, it's going to be deflected towards Jupiter, away from the Earth. Now that's an example of divine design. You want to hear a really big dramatic example of that? We go to the Shoemaker-Levy impact in 1994. It's a comet. It was a big comet, huge comet, and what it did is these pictures were taken by the Hubble Space Telescope. And what it did is it initially passed Jupiter on a wide elliptical orbit. It's like an oval, giant oval. It goes past Pluto and then circles back and comes. So we've seen it go past Jupiter. So they do computer tracking. So it's going to come back in 2 years and it's going to hit Jupiter. We know by the celestial mechanic trackings, by equation, by Newton's laws of gravity. So this is when it came back. This is a sequence. This is the Hubble took sequential pictures. It's several hours. Okay, so it's on its way. It broke up as it came near Hubble the second time closer. It broke up in pieces. So it's going at a velocity of a little over 137,000 miles an hour. So as it's heading towards Jupiter, this is the first impact. These are the second impacts. This is the third impact. Each one of these impacts are bigger than the Earth. So that was a good thing that Jupiter drew it in. If it was hit by the Earth, we wouldn't be here. It would have obliterated the Earth. Saturn, we go to the next planet, Saturn. Okay, Saturn essentially does the same thing to a lesser degree, but still enough. Saturn is farther away. We have Saturn at 894 million miles away. And that means when you look at Saturn, you're looking at the light that left it 45 minutes ago instead of a half hour ago. Saturn is a little smaller than Jupiter. It's 800 times bigger than the Earth, so you can put 800 Earths inside. Saturn has these rings. You see these rings. These rings are composed of particles. The smallest particle is a particle of a stone. The biggest particle is a particle of a van. So there's millions of them. And astronomers think that used to be moons going around Saturn. And over the course of many years, the gravitational pull of Saturn broke these moons apart into many tiny pieces. That's why you have it. It looks, they look solid, but they're composed of thousands of particles. When space probes go take pictures, they fly either above or below. They can't go. They'll be smashed if they go in. So interesting thing about Saturn, and that's a gaseous planet too. There's a lot of hydrogen as well. And they also have the northern lights in Saturn too. Up here and down there. And I've seen pictures of those. And this is called the Cassini. This gap is called the Cassini division. It's 2,200 miles wide. You could almost fit the United States in it. That was discovered in 1675 by Giovanni Cassini, an Italian astronomer. He's seen that division in his telescope. So this from here to here, it's 2/3 the distance from the Earth to the Moon, about 200. So the Moon's average median distance is 238,000 miles. So this is almost the distance from the Earth to the Moon. But when you look at it through a telescope, it looks small because big things look small if they're far away. Yeah, so that's Saturn. I've seen Saturn, many times in my telescope. I've seen pictures of the Voyager going like a vertical. They could shift its trajectory. It's going around, but then they could go at an angle, go up and down. They shifted the gravity. They go a little closer to Jupiter, and the gravity can accelerate to 76,000 miles an hour. I've seen a lot of pictures of that, and it looks like it's going slow because Jupiter's so big. We're going to move on. Let's move on first to the Milky Way galaxy. That's where we're residing. Milky Way galaxy is